I would never start a conventional car company. Never, ever, 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 because I did that once before. It's fundamentally broken. When you create a totally different way to design and manufacture and assembly, the architecture of the product, the product's performance, almost all aspects of it are going to be totally different. So at the start, it was a development platform connected to that set of digital manufacturing tools.
Hi, everybody. Welcome to Horsepower Heritage. I'm Maurice Merrick, and greetings to all of you listening from places like Buffalo, New York, Miami, Florida, Louisville, Kentucky, Schaumburg, Ontario, Canada, Hobart, Tasmania, and Kanpur, India. Thanks for joining me, and if you're a regular listener, you know we talk a lot about automotive history on the show, but today's episode is all about the present and the future, and I think you're going to be amazed by what you're about to hear. Kevin Czinger and his son Lukas have rewritten the entire concept of design and manufacturing, not just for the automotive industry, but for aerospace, machinery, and probably any durable product that has component systems and moving parts. Their company is called Divergent Technologies, and they're building hypercars, the Czinger 21C, the VMAX, and soon the Hyper GT. But here's what's so different. The cars are designed using artificial intelligence. The parts are 3D printed, and most of the assembly is done by a robotic factory module. So there's no conventional assembly line, no castings, no stampings, no tooling, no nuts and bolts. And the factory module is about the size of a 2-story single-family home. It has a shockingly small footprint. Every aspect of product design and manufacturing is on a compressed timescale, and it's incredibly resource efficient. And I think it's going to change everything. The implications are so broad and so deep, it's like the telephone versus the internet. So I hope you're as fascinated by this one as I am. By the way, don't forget to click that follow button, leave me 5 stars, and just a short review, even if it's just a thumbs up on Apple Podcasts, because that really helps the show. And pass this episode along to a friend who might enjoy it. I'm pretty sure that this is the most in-depth interview that Kevin and Lukas have done together. We sat down at Divergent's headquarters in Torrance, California, in a conference room overlooking the factory facility. And they also gave me a tour of the cars, as well as showing me some of the 3D printed components. And it was like holding a piece of alien technology. It was familiar, but also otherworldly. And I'm not exaggerating. It was just amazing. And if you follow Horsepower Heritage on Instagram, you'll be able to see what I'm talking about. And also subscribe over on YouTube, because I'll be putting up some videos there too. It's a deep dive into the future with Kevin and Lukas Czinger. And that's coming up right after this. Hey guys, here are 3 scale model exotic cars you can find right now at modelcitizenddiecast.com. First, it's the 1974 Lamborghini Urraco. Second, a Lamborghini Countach 25th Anniversary Edition. And third, a 1992 Bugatti EB110 Supersport. 3 great exotics to start your model car collection. They're all in pocket-size 1/43rd scale, so they're easy to display just about anywhere, from your desktop to your dashboard. Go to modelcitizenddiecast.com and use the promo code HPHeritage to get 10% off your order. Limitations apply. From race cars to street cars and everything in between, it's Model Citizen Diecast, because your inner child still wants to play with cars.
Thanks for having me in, guys. I am incredibly impressed. I want to talk about these cars, you guys. There's the 21C, right, which is named for the 21st century. That is the track spec car.
Yes.
The 21C VMAX is the road car.
Yes. More of a long tail look.
Right.
Higher top speed. But the 21C in its high downforce spec, just the original 21C, is also road legal. So you can really drive either one on the road. One is just more aggressively really designed for track performance. And the other one is a little bit more elegant, lower downforce, higher speed vehicle with more of a grand touring interior but still a dominating car, same powertrain as the 21C.
And then down the road a piece, you're looking at producing the Hyper GT, which is a 4-seat Grand Tourer.
Correct.
But let's start with the 21C because the layout, the power plant, everything is sort of unexpected, right?
Yeah, I think, when you have a new technology that's so radically different, and when you also are creative people like Kevin and myself and inspired people, you look and say, what sort of vehicle do we actually want to put out there? And pretty quickly, we said we want to make the world's most high-performing vehicle, the fastest vehicle, the vehicle that really pushes this technology to the absolute limit and showcases it as well. And that was really the initial genesis of 21C, was how can you make something that breaks every measurable record in the hypercar universe, showcases this technology, and also further develops this technology. So in the 21C, the performance is really unheard of and setting a new benchmark, but also there's a ton of novel systems in there, from the fully printed transmission, fastest 7-speed ever made, to the world's most power-dense California CARB emissions compliant V8 ever made, right? These are systems that were developed ground up because we were making a car that just had to outperform everything else out there and fully leverage this tech. So, in terms of team, you're talking about really world-class engineers coming out of F1. You're talking about world-class engineers coming out of aerospace and defense. You're talking about people coming out of Apple and Google, right? This is not your typical auto engineering team. This is new tools, world-class team from all different backgrounds, all going after this mission of what is the highest performing car we can make. We're only making 80 of them. So we see this as really the object, right? The physical object in the world that for the first time demonstrates this transition from analog manufacturing to digital manufacturing. And now it has all the records to go with it as well.
And so the seating in the 21C is an interesting configuration.
Yeah, I think, form follows function in a lot of ways here. I think there's an emotional sense to being centered in the car, which is just amazing from a driver standpoint. Left-hand turns, right-hand turns, you're symmetric, you're on the track. That's the best driving position by far. I don't think there's any argument with that. You've got your co-pilot behind you. It's actually quite an intimate experience. It's like you're in a fighter jet. They've actually got a ton of space back there as well. So from an ergonomic standpoint, it's great. But from a performance standpoint, that's really one of the main drivers as well. You have that, cockpit, you have that glass canopy. It has very little frontal surface area, right? It's essentially half as wide as if it was a side-by-side vehicle. And that allows you, one, less frontal surface area, but two, more area, more volume on the sides of the car and under the car to actually do your active aerodynamics work. So again, we just said, hey, this is a competitive advantage we can have here. We can actually use all that space to engineer an aero package. And we did. Nick Alcock, who's our head aerodynamicist, was the head aerodynamicist at Williams F1 for a long time. This car now does better than 3.5 to 1 lift to drag in a street legal body. So this is really LMP type aerodynamics, but on a street worthy vehicle. And that canopy, that 1+1 seating, big driving factor for how we achieve that.
And the car has an in-house designed twin turbo V8, a little under 3 liters, I think.
Yep, 2.88.
And it's a gas electric hybrid. So you've got electric motors at all 4 corners, or
just the front 2, and then a third electric motor in the middle, which acts as the starter, and we call it the motor generator unit. Kind of connects the whole system here in a strong hybrid configuration.
And it also can regenerate as a generator the battery packs through the crank of the internal combustion engine motor, or it can draw energy from those packs and put another 150 horsepower through the V8.
As a electric boost for the...
Essentially, yeah. Yeah.
And regenerative braking as well.
Yes. So the braking is really turning the EV motors into generators, which then, brake the car, because obviously the motors need to be turned by the wheels as a generator, recharging the batteries, or then taking energy from the batteries and driving the wheels. And also that motor generation unit, the third electric motor or generator, is on, the front crank with gears on the V8. And so that can either, as a motor, take energy and put 150 horsepower through the internal combustion engine, or as I said, also be used to regenerate the battery packs.
Up to 1,350 horsepower, is that right?
Correct. Yeah.
Yeah.
I'd say that's a very conservative
Yeah.
number, actually.
And you guys set the lap record at Laguna Seca for a production car.
Yes.
The lap record at Circuit of the Americas.
Correct.
How exciting was that?
I mean, I think it was, incredible. There's a certain experience of making technology and inventing and great IP, but there's a different feeling when it's a physical product and you experience it and you see other people react to it as well. And rarely in life, I think, is there just such a proof in the pudding sort of moment where years and years of engineering and risk turn into developing a product, and then that product performance can be judged in a lap that takes a minute and a half, right? And you see all of that add up, and you see that car go over that finish line, and the times it's achieved, it's incredible.
Yeah, I mean, if you see photos from it or YouTube videos, obviously, you see the kind of emotion that you see when, athletes as a team would have trained for years. You have the, pure joy of winning a competition, and that's what you feel. I mean, it's a great feeling if you're a competitive person who's had the discipline to, train as a team or work as a team, create as a team, build as a team.
I know you guys have a professional driver on the team, but you took your own laps around the tracks, right?
Of course. Yeah. Sure. No, of course. I would say in the future, we have some ideas about some events that we might do together as a father-son team. I mean, doing those lap records, though, our board of directors has forbade that we ourselves do that. We use Joel Miller, who's also Ferrari's factory driver and is a terrific driver.
What were his insights on driving the car? Do you recall what he said about the experience?
Sure. Laguna Seca was the first production record we set. And he, a week earlier, actually, it wasn't even a week, it was days earlier, had been with Ferrari at the Indianapolis Speedway road course and had set the production record with the SF90 Stradale Ferrari hybrid vehicle there. And he came back and, when we opened up the door, he just said, Kevin, this car is levels beyond any production car that I've ever driven. I mean, it is, what I just drove a couple of days ago is in no way comparable to this. I mean, at a Circuit of the Americas track with that long straight where you're going 190 to 200, I think it's generating around 5,000 pounds of downforce on that vehicle. You are absolutely glued to the track. And then the other thing that he said was, this car, just the way it feels, and actually Jay Leno, who's a driver, said the same thing. He's like, this car has soul.
Yeah.
And, that's what, if you're an athlete, if you're a creator, engineering, design, competition, you're talking about, AI things versus human things. If AI is a tool that is being used by you, you can use that to create things that have soul. It's not going to be created by AI. It's going to be created by a human team that uses those tools. And that's exactly what we wanted to capture.
It's fantastic. So, Kevin, I know you have a long and varied background, Wall Street, all sorts of different skill sets. But being a car manufacturer is really expensive and risky. So why take the chance?
Well, we created tools that make it magnitudes less risky and magnitudes less costly. And really the idea was create a totally different set of tools, digital tools, that could have an impact on making complex products like vehicles much simpler, much lower cost, much quicker, much less capital intensive, and basically digitalize that product creation of the physical world in the way that we've digitized the content world. And so once you have those tools, it completely changes the capital and risk of a car company.
So holistically, it was an entirely new approach.
Yes, I would never start a
conventional
car company. Never, ever, 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 because I did that once before. It's fundamentally broken. I was the co-founder of an EV car company. Lukas worked on the assembly factory floor back 2008, 9.
Yeah, right around then.
Yeah. And we learned from that we need to move from the typewriter level of manufacturing to Mac desktop publishing and digital manufacturing.
Yeah, I think that's really, the first thing to understand is we started as a tech company that was informed by lessons learned out of the automotive industry, but we certainly didn't start as a car company that was going to take a vision for a vehicle and bring it to life and, trying to outcompete traditional car companies as, the usual EV startup story goes. What we said was, Kevin has a set of learnings. I've got a background in engineering. We've got an idea for a technology system that could fundamentally change automotive, aerospace and defense, a lot of other industries as well. We're going to take the risk of developing that technology, which I'd say was very risky, and we're not risk-averse people. So we went for that, and we first set out on that mission of design software, additive manufacturing, and materials assembly, generated over 550 patents over that 4-year period of high-risk development. And then once we had those tools, that technology, then we said, okay, we love automotive. We've always wanted to start our own car company. Now we actually have a backbone to build a really successful company, which, knock on wood, is Czinger Vehicles here.
And a lot of people aren't going to be familiar with Czinger. There's certainly fewer people probably that are going to be familiar with Divergent Technologies, which Czinger was an outgrowth of Divergent, right?
Yes. I mean, when you create a totally different way to design and manufacture and assembly, the architecture of the product, the product's performance, almost all aspects of it are going to be totally different. So at the start, it was a development platform connected to that set of digital manufacturing tools.
And you're capitalizing on a lot of emerging technology. For example, additive manufacturing, or as most people know it, 3D printing, right? Kevin, was that the seed of Divergent?
The seed of it goes back to when I was, a teenager and first learning about technologies and looking at how you would create a universal constructor, something which would simply take in a set of requirements for a product and then be able to, without metal bashing, generate that product. And that is like background set of aspirations, right? Like Star Trek fed aspiration of like, what is the future of being able to imagine something and materialize it?
Right. Like the Star Trek replicator.
You got it. That's it. Exactly.
Yeah.
But the Star Trek replicator was based on John von Neumann, Nobel Prize winning physicist and mathematician who Einstein said was the smartest person who ever lived, who had actually written extensively on the future of creating universal constructors or replicators and what that could look like. And that had always been in the back of my mind since the time that I was a teenager and curious about these things. And then as my life progressed, certainly that real breakthroughs in applied science don't happen because there's a single technology like 3D printing. If you isolate that as a technology, it doesn't have very much power. All of these real breakthroughs in applied science have occurred when you've taken a whole collection of technologies and then use those together in a system where each of the technologies is mutually reinforcing the other technologies. And so what happened was, as Lukas said, we had that experience designing and manufacturing electric vehicles in a joint venture in China, around the late, 2000s, 6, 8, 10. And looking at that and saying, now we do have processing power. now we can generate against multiple constraints something that's just not a flat sheet of metal being stamped, but within 3 dimensions, simulate all of the requirements and generate something that's truly optimized, and then materialize it and assemble it, and take a clean sheet of paper and all of those different elements and do that. And so really it's looking and, against the development of different technologies that you're seeing, against a big idea that you have, against understanding that you have to approach things from a system and seeing a big problem. Like, obviously our entire world is based on automotive travel, right? Our entire physical built world is around that, and it's completely unoptimized. It's completely uneconomic. It's environmentally super destructive. Now, how do you take those big ideas and create the first concrete instance, and then create an object with those tools, a car? And as Lukas said, that is an enormously audacious and risky task.
For sure. I mean, you're basically rewriting the entire book. You guys are the biggest disruptors that I can think of right now, and that's exciting.
Maurice, we're doing the best we can. I won't argue with you that what we're trying to do is audacious as you can possibly be, but at the same time, as you're doing this, and it was really invent or perish, literally, everything from software to materials to automation. Lukas on the automated assembly cell, a digital way to assemble. He was the lead inventor with 44 inventions. Like, literally, there are things that if you hadn't been able to invent them, you wouldn't have a system, and none of this vision would work. And as you do that and put in the time and you build the team, it can only make you, at least for me, only make me feel more and more humbled by the task and, inspired to try to make it happen.
Let me ask you guys about risk and setbacks, potential failure. We all fail, right? That's how, by definition, it's how we learn, is by not getting it right maybe the first time. You're highly successful, highly motivated. You've got a visionary approach to what you're doing every day. You have to have the 50,000 foot view, and you have to have the microscopic view, all at once.
Sure. I'd say, one, Kevin and I are obviously very different in age. So in like a very calculated, logical basis, we probably have slightly different views on it. When I started, 6 years ago, I think I was around 22 years old. So I just gone to Yale, studied electrical engineering, graduated, started working finance, doing investment banking, M&A, which was the bank I really wanted to go to, was the highest paying job, was kind of the career path that most of these Ivy kids were on, and seemed very, steady and interesting to me, and very lucrative. But, earlier than I expected, I always thought I wanted to work on something that would be disruptive or have a big impact on the world. I just didn't know when exactly, right? And earlier than expected, Kevin had the initial idea for Divergent. So I looked at my life and I said, I have this banking job, I've got this background, but now I've got this opportunity that came way quicker than I thought. What do I do? And for me, it didn't take me long to say, I want to be, a part of that vision. I want to commit myself to doing something that could change the world. I want to work with my father and, take this from 0 to 1 and put my all into it. And I'm willing to take the risk of it not panning out, right? And that was, my initial risk-based thought was just betting on us from the get-go. Since then, it's a long-term race, right? It's 6 years plus. There's going to be many, many years of this company left. How do you every day, deal with that amount of uncertainty as well? And I think that is purely, part of it is passion, right? Passion for what you're developing, passion for, your own interest, intellectual interest in it. And then part of it is very much so for me, mission driven, which is, if it does succeed, what's the impact on yourself, on your family, on the world? I think part of it is having Kevin work here as my father, right? It's being motivated to make him proud in a certain degree, but also, to make this work for him, because I know his age, I know his life story, and I know how important this is to him as well. So there's a lot of, I think, drive that, the two of each of us gives each other in this project as well, in this company as well. And then the last piece is just having faith in, your ability to continue pushing it, and faith in your ability that, there is some power greater than yourself that you need to embrace and just, continue on that mission that's most meaningful to you.
No, I think it's very important. It fits in perfectly with the show. Kevin, I've read a number of places that you're a big fan of Kelly Johnson from Lockheed and the Skunk Works. And I wanted to touch on that for a minute because this is a Skunk Works here. Was there a management philosophy that you learned, or was it just the fact that that guy accomplished so much in his career?
When I was a teenager and going to the local Carnegie library, I grew up in the youngest of 5 in a very working class Cleveland family where I ended up being the first to go to college, but there was a library close by, and I would go down there, and I was extremely intellectually curious. I am a voracious reader, and my 2 older brothers were car mechanics and built race cars for the street and for the drag strip. And you're growing up as a kid, and if you're building things, you're like thinking, wow, what are the coolest things to build? And you're starting to read about those things. You go back, start going to the library and looking in the card catalog to see what's cool to read about. And just looking at the SR-71 Blackbird, which, Lukas and I together, he mainly built as a model and then hung from the ceiling of his bedroom when he was young. But you see that plane and you go, wow, somebody created something absolutely remarkable. And I'm a voracious reader, so I was reading everything. And then I later found myself in Silicon Valley. And, you start thinking about management, and probably the 2 biggest influences on me were Kelly Johnson's memoir, More Than My Share, which has his 14 principles around which he built a 1950s Cold War Lockheed Martin Skunk Works. It's obviously vastly changed since the day that he said to them, I want the full budget you're giving me to build a plane that's going to go 3 times faster, cruise 3 times faster than the top speed that's been achieved by an air-breathing manned aircraft ever, and I'll do it in 20 months, but I'm going to take 1/10 or 1/15 of the people, put them all in one building, and we're going to work as one small, super high-powered team together that does the full cycle of R&D and production and testing, and then actually does it. And that's what those principles are around. That, and Andy Grove, who had a book that's called High Performance Management, which, I later had, blessed good luck of meeting Andy and spending some time with him when I was in the EV car manufacturing business. And, he, although, you meet him and he had very thick glasses, he was, really the CEO who built Intel, and created that modern Intel microprocessor industry. He wrote a book about teams and managing the way that a coach of a great athletic team would coach his team. And I always thought, from my background, and both Lukas and I played sports through college.
You were a football player, right?
Yeah, I was. And, that combination of the power of the small team, and coaching that team, with the first principle always being, you never take credit for your players. They're always out in front of you. You're always building the team. Those 2 books that I read early on in my technology, entrepreneur career in Silicon Valley, those are the 2 that really have most influenced me. And obviously, if you walk around here, you'll see if people are interested in them, we hand these books, out to employees that come to start to work for us.
Fantastic. What was your sport, Lukas?
Soccer.
Oh, okay.
Yeah, a little different, but Yeah, we both went to Yale, and obviously a couple of decades apart, but actually some of Kevin's teachers and some of the athletic staff remained. So we actually had shared. I think the guy that did our equipment locker room was still there by the time I got there, and I remember getting my jersey the first day. He's like, "Czinger, is that Kevin Zinger's son?" And I was like, "Yeah, that's me." So, really, really fun.
That's a cool continuum.
Yeah, it is for sure.
Yeah.
It was really wonderful.
We've taken 150-year industrial legacy in the United States, and we've offshored it.
Mm-hmm.
I would really like to know your thoughts on that. The technical drain in some ways that's occurred. It's a different world, free markets, all of that. I get that. But what's significant and is not lost on me is that you guys are manufacturing here in the United States. And it's clearly important to you. What are your thoughts?
I mean, I grew up in Cleveland, and Cleveland at one time, was a manufacturing powerhouse. And in terms of Fortune 500 corporate headquarters in the 60s, it was one of the couple centers in America, particularly for manufacturing companies. And what you saw was, as people planned on shorter time frames, driven by quarter returns, when capital equipment became obsolete, they had to make a decision. Are we going to allocate very large amounts of long-term capital into that, or put it somewhere else that was, a low-cost center? And from the company standpoint, there may have been a logic to that with all the factors I'm talking about, including those quarter-by-quarter earnings management. But from a community standpoint, it was devastating for the community, devastating for Cleveland. The second thing is, when you're looking at the knowledge base of the country, and this in particular was something that Andy Grove, toward the end of his life, 2010-ish, focused on. He said, microprocessors are not only the design, they're also the manufacturing. And that manufacturing knowledge, when it gets offshore, you're losing a very critical knowledge base over the long term. And when I started this company, those two very core thoughts and experiences were in my mind. And I looked at this and said, the best model would be to create a permanent manufacturing footprint in communities. How do you create a permanent manufacturing footprint? With a system that can digitally learn and adapt itself, so it never becomes obsolete. That's what a digital system is. That's why Divergent is called a Divergent Adaptive Production System. Already on Lucas's, the subsystem that is the vertical assembly cell, we're using the system itself to design and manufacture parts of that system. So my long-term goal is to create stable, regionalized or relocalized manufacturing where that community ecosystem continues to grow and adapt, and the factory's DNA, the way that it's coded, its software allows it to learn and adapt the hardware, along, with those evolutions of the software. That is a full digital adaptive production system, a permanent manufacturing footprint. That to me is healthy. That to me builds community, stability, jobs, the job ecosystem around manufacturing, the creation of things locally or regionally, the cycling of resources locally or regionally, the educating of people, whether it's community college, apprenticeships, or university, all around that. We need stability today.
No, I agree completely. I think, environmental sustainability is such a big aspect of this company as well. But, a lesser talked about one is probably social sustainability in general, and in the U.S. as well. And Kevin lived through that kind of offshoring model. I'm now living through the onshoring model, right? We're seeing the conflict that we're having with various countries bringing technology back to the U.S. and putting a focus on build locally and build and employ your local population. And regardless of your political view, this divergent factory model allows for that. It allows for every city, every major population base to have the latest technology at their fingertips to design, manufacture, and assemble in a factory that won't be outdated 5 years from now. It'll just keep progressing. It'll be, even more advanced 5 years, 10 years from now, and have more jobs associated to it. So I think at its kind of peak or at kind of the most center point of the vision, this is a company that can create a lot of social sustainability, create a lot of jobs, and do it in a democratized way, right? We're not sitting on that technology ourselves for our own economic benefit. We're trying to let everyone in the world essentially access it through this factory as a service model and deploy these factories in every local community. And I think for us also, it's kind of world citizens, but American citizens as well, there's something to be said for generating that amount of IP and technology out of the U.S. as well that makes us proud, makes a lot of the people here proud as well.
Lukas, you mentioned IP, intellectual property. One of the probably your top priorities is to protect your IP here. Mm-hmm. Because then, as you said, Kevin, earlier, once it's offshore, you don't control it. How are you able to do that and still share?
One of the beauties of our business model being factory as a service is, say we have 10 factories in the U.S., Divergent owns and operates those factories, and we version them, we run the software in them, we run the machines in them. So we actually don't have to open the black box for anyone to look into and gain that IP knowledge or those trade secrets. But at the same time, they can have the product of that black box and they can build their businesses using that black box. So they gain all the advantages of it without us losing any of the IP or letting them look into kind of the back end of the system. So just from a business structure standpoint, there's inherently a lot of protection by keeping that black box closed. And I'd say from the very start on IP strategy, we've just been very, very diligent on mapping that white space, on getting what we call gating patents that would stop someone from entering that space in general, and then protecting them with the most relevant and valid claims around each of these inventions. So the IP mode is great, but I'd say even more than that, the business structure allows us to keep it safe.
So company A comes to you and says, we'd like you to manufacture these widgets that we are conceptualizing at this point. So you can work with them from the ground up.
Yeah.
Step one, just the digital end of things all the way to shipping.
Even almost before that, right? Where we come in is at the concept stage a lot of the time. Here's the requirements for what I want my product to be. It needs to be this strong. It needs to have this durability life. It needs to take this crash load. It needs to support these features. We'll say, okay, let's turn that into a document that fully defines that product. Then let's feed those inputs into our design software, which actually Pareto optimizes against each of those key inputs. Then we'll have that design, and they'll have given us the input requirements or the design criteria that's important to them, but our software will actually optimize that structure, that part against those, and we won't open up the back end of that software. We'll then manufacture it in our own materials on our own printers and assemble it with our novel assembly cell. In the end, ship those units, whatever it is, 10, 100,000 to that customer, perfectly optimized for that customer's requirements, and they're very cost effective. And that customer hasn't taken on any of the CapEx, the upfront expenditure to build their own manufacturing facility. So economically, they've de-risked their business and they've gotten something that is higher performing than with any other technology that they could have gone after.
Obviously, information, in the cloud is global, right?
Right.
But the actual physical world is local. Imagine if you have a regional network of factories, people who want to create something simply have a set of tools. Just like a game developer in the late 90s, they would have had to create their own tools and then create their own server infrastructure. Today, they can get a set of tools, say from Amazon Web Services, generate something, and then in the cloud, they have computing power, processing power, and storage. Because the tools end of that is in the cloud and the information, we provide that globally, but then locally, you're creating things that can be used locally in the local physical world. So imagine anyone almost anywhere on the planet is able to access the most cutting edge data and set of tools to say, this is a product, I may create one or I may create a million. I don't have to worry about that right now. I just have to think about that product. I've got a set of tools that can generate that. And then when I go to manufacture a first prototype, it's not like I have to raise some insane amount of capital. The means of production no longer have a barrier to that person. And so you localize that, you remove that barrier, you give them the creative tools, and then you build locally in that community, well, innovating globally through the cloud, providing global innovation access to that information.
No, it's very exciting. I mean, anyone who's ever had a product idea and has investigated the cost just to prototype. So the parts that are sitting on this table in front of us, they have an almost biological appearance to them. They're very organic. And this is because of AI, right?
It's because when you're telling a machine, and a machine has the processing power to simulate something and say, against this set of requirements, forces, durability, stiffness, crash, other elements, make things in 3 dimensions, not 2-dimensional stamping, but in all 3 dimensions, add and subtract material until it's perfectly efficient for material and energy against those requirements. You know what else does that? Evolution. But it takes eons of trial and error, in a physical constrained environment. But then we have the fantastic looking flora and fauna structures that we see around the world, right?
Right.
Well, that's why that looks like that. You're using that computing power to mirror evolution in microseconds and make optimally material and energy efficient objects.
No, agreed completely. I think these structures look biologic because the AI programs we use are competing for material in the same way that biology does. And you can guide that to a certain extent as well if you want to design, enhance any of these parts. But really for us, these are chassis parts, these are performance parts. So we end up usually picking the most optimal design, the lightest weight design. And that's one of the benefits of the system is we can support the same requirements, but with less material. So when you talk about environmental sustainability as well, we can essentially make the same structure, but with 30 or 40% less mass to it, which means 30, 40% less aluminum and other raw feedstock going into that design. And these structures, they look unlike any other structure in the world because 1, they're designed with a novel software, but 2, they're manufactured with additive manufacturing, which allows you to break all the geometry constraints of a stamping or a casting.
Yeah, fascinating.
And at the end of their life, just like say you'd have an alpine meadow that's undergoing evolution over a period of time, but it's cycling all of the materials, H2O, CO2, phosphorus, nitrogen, all of these materials that are designed in-house here, all can be at the end of their life reatomized, turned back into a printable powder and reprinted as a new structure. So you're both using the minimum amount of material and then you're cycling it through the system. And over time, the objective is to, cycle that material locally through a system where you really don't need to mine new material again.
Kevin, what's this part right here in front?
Well, probably Lukas is the best to explain what that is.
Yeah, so that's what we would call a node. You want to pass it to me?
Hold on over.
So a node is essentially what we would call one printed piece that's going to go into a larger assembly. So this node is actually part of that frame that's sitting over there. But this is essentially one unit, one Lego block that we would assemble. So 3D printed in our own aluminum alloy, and then very importantly has a lot of different features, which we can't go into full depth on, but I can point out a few that support our structural assembly strategy or our manufacturing strategy. So we join structures by using polymers, adhesives. We don't do any welding. So there's a joint architecture, double shear architecture that we've invented and use. There's actually separate pockets in here for different adhesive types. There's features that allow that adhesive to cure more rapidly using different curing sources. And then there's gripping features that actually printed directly into these parts as well. So the robots interface with a 3D printed part. And then there's other features which are for metrology systems to actually reference, because we're not doing any sort of fixturing or tooling for our assembly process. It's all essentially mid-air and guiding robots into position using the parts as reference data for the measurement devices. So this essentially is one unit fully designed by our software, manufactured here with all of our assembly and manufacturing features directly incorporated inside of it.
So imagine a system where within the design space, against all the constraints, including manufacturing and assembly, it creates a perfectly optimal structure while at the same time generating its manufacturing and assembly instructions, then breaks it into Lego blocks, prints the Lego blocks, and those Lego blocks in a system can self-assemble because all of the assembly features are built into them. And you can do it at aerospace level accuracy and auto volumes, which are basically the highest volumes on the planet, and do it in a modular way. That's the architecture and structure we use. In addition to that, with these structures, we start to make them even more efficient by merging one system into another. We call it functional integration. So say you take a brake caliper and a suspension upright, instead of having separate pieces with many fasteners and hydraulic lines, all of that is printed in the structure. So you're taking, in some cases, 40% or more of the mass out of the structure, obviously much more mass and energy efficient. You're increasing its stiffness. You don't have all of those parts. And all of that means you can be much, much more efficient in making the product, and the product itself is more efficient, right? So then, as you're thinking about infrastructure, how much fuel do you have to generate? How much electricity do you have to generate? All of that starts to be compressed. You start to compress material and energy flows on a global level, and you start to collapse the infrastructure, material, and energy requirements.
Yeah, it's fascinating. The integrated caliper and suspension upright, it simplifies everything that I can think of about the automotive sector, from the manufacturing point to servicing the vehicle and everything in between. It's revolutionary.
Exactly. Then in terms of repairability, you just have brake lines where the things are bolted together into sections. Something gets damaged, unbolt that section, bolt a new section on. In terms of inventory safety stock of replacement parts, you simply have data. You need a replacement part, it gets printed and assembled. Do you need to keep tooling for a long period of time in order to stamp more things? No, you simply have data that gets sent to a machine anywhere on the planet and gets printed and assembled. So over time, it will make for a very compressed and much more efficient supply chain for sure. I think one thing we saw very interestingly was in the past 6 months or so, we had General Atomics, which is a very large defense drone maker, come to us and say, we have this small unmanned aerial system. It's a little under 3 meters long. It took us about 3 years to develop this system. Each one of these systems takes about 12 days to do with hand laid up carbon fiber shell. They gave us the CAD. Within 4 months, we had flight-ready hardware for them. And we had reduced the number of parts by integrating in an annular fuel tank, heat exchangers, other things. We reduced the number of parts from over 140 to 4 parts.
Wow.
And the assembly process took, how long does it take to assemble that? A couple minutes.
Yeah, minutes.
Unreal.
And then shortly after we provided them with the hardware and they saw it, they announced that we were their partner for manufacturing, these unmanned aerial systems.
Wow.
They've been taking this around and showing people and saying this is the most dramatic disruption anyone could imagine for the defense and aeronautics industry.
Yeah, and of course, it's immediately applicable to full-size piloted aircraft, right? I mean,
to parts of them.
Yeah.
I'd say at the start, because of the long commercial qualification process, it will first be applied to unmanned, I'd say, air, land, sea, and space systems.
Mm-hmm. Is anyone doing what you guys are doing? Anyone else?
No. I think, long answer, short no. I think our approach is just very different than others, which was system from day one. Do it start to finish, be the people creating the tools, but also using the tools to make the product, and design software plus materials and AM plus assembly all integrated together. There's people that are doing point solutions along that roadmap, right? They're making a design software or a material you can print or trying to make a faster printer, but none of them have that full systems approach, and therefore none of them can actually supply you with a product like that. So we're the only ones in the world that can make a product like that rear frame or the fuselage structure of that drone that Kevin mentioned, and that's because we're the only ones that built that system.
I'd say this is a massive amount of work and risk to do in a very compressed, Kelly Johnson SR-71 period of time. And, respectfully, and I hope I don't sound too arrogant, but I am very proud of what the team did. We've actually done that.
You have every right to be proud of it. Kevin, you made a very logical analysis of pure EV automobiles, and you concluded that that wasn't the way to go for you. Can you talk a little bit about that process and where you ended up in terms of power plant?
I mean, first on electric vehicles, you see, you're using what is currently the most advanced battery chemistry, the different lithium-ion family battery chemistries. So, lithium is the third element in the periodic table, so it's light. And when you're talking about density, the energy density, the amount, the number of kilowatt hours that can be contained within a given mass and a given volume factor, that's very important because a car can only be so large, right? And so heavy. And so you're looking at that and saying, given those physics constraints, you're manufacturing this system. And, when you manufacture it, you have to look at what the manufacturing emissions are. Having actually been involved in, if not the first large format EV cell design and manufacture, pack manufacture, thermal management system, battery management system done at scale on the planet, it resulted in building the first 1 million square foot EV battery mega factory in China, because at the time I couldn't find partners other than the Chinese central government to do it. But one thing I learned from that was when you're manufacturing things that are very, very energy intensive, like the cathode of a battery system, and you're using coal-fired power, it is, very, very polluting from a CO2 emissions standpoint. And so, that factory then was used as the template for China to scale up lithium iron phosphate batteries. Almost all of those factories, if not all of them in China, use low-cost coal-fired power. They're emitting 200 to 400 kilograms of CO2 per kilowatt hour of battery cell manufactured. And when you take the low end of that range, 200 times, say, a 90 kilowatt hour Tesla, Tesla probably uses over 50, 60% of their batteries are CATL, China manufactured battery cells. 200 times 90 is 18,000 kilograms of CO2 emitted in the manufacture of that battery system, if we're talking about the low end. Of course, there are factories in different places that use nuclear power or use some type of renewable energy. But the fact is 80% of those batteries that are currently manufactured do use that, right? If you took a Toyota Camry and you looked at what the grams per kilometer CO2 emission is, so say you take a Toyota Camry, you drive that 80,000 miles, and it's generated less CO2 than just the manufacture of that battery before it's ever charged with whatever source. So you're looking at it and you're saying, what does it mean? Who is actually going to produce these? Who actually has scale? Who controls the supply chain of lithium and cobalt and nickel, which we know is mainly controlled by China? Now, who has the lowest cost? I mean, there's a reason Tesla is buying all of these cells from China. They're using coal-fired power. Well, let's be realistic. You can't build a 90 kilowatt hour car with a long range, or a pickup truck that's 180 kilowatt hour battery that can be double, or sometimes you're looking at a Hummer that's, EV Hummer that's over 200 kilowatt hours. And if you're realistic and you're not messing with the model, if you're not saying, oh no, the car only has a 30 kilowatt hour battery pack, and we're building it at Northvolt in northern Sweden using hydroelectric power. If we're looking and saying, here's the core, here who has these resources, then we should admit on the face of it that is happening. So I say the question isn't, am I for or against something? I am for fact-based analysis where we don't go, wouldn't it be like marvelously wonderful if we had this magic thing called a lithium battery, and that lithium battery allowed us to consume as much material and energy as we wanted, and we wouldn't have to worry about it? Like, no, please, let's not follow some kind of fantasy that we're having. Let's deal with facts, because if you scale up something where the manufacturing pollution is worse than the tailpipe pollution, given where it's being manufactured, you are not going to reduce environmental impact. You are going to accelerate it. You're also going to change where things are manufactured and who controls that supply chain. So let's be real. And by the way, right now, I'll use, Elon Musk's target for what the battery industry should be producing each year. In the last year or so, we manufactured globally about 200 gigawatt hours of EV battery cells, right? To have like 50 to 60% of the EVs be, or 50 to 60% of the car fleet be EVs, Elon Musk is saying we have to manufacture 300 terawatt hours. Now, if you take 200 gigawatt hours and say how much more is 300 terawatt hours, it's 1,500 times. Now, that means magnitudes more mining, magnitudes more production, magnitudes more power generation. Have we actually looked at that? Who is going to produce these? When are they going to produce it? Not, have we found a policy expert who's taken a single model, put in a 34 kilowatt hour Nissan Leaf from 2013, which I've seen, and then put in the Northvolt factory in northern Sweden, which I've seen at the federal government level? No, let's be real. And if we're real, what we should say is look at a diversity of technologies. That's why Europe, Germany in particular, with smart people who I talk to, like Mercedes, VW, Audi, Porsche, are like, there are e-fuels that are drop-in fuels that can be dropped into any of these cars retrofitted, that can be dropped into fueling stations. There are a variety of solutions we need to look at. And so I would say diversity of solutions is important, and realistic modeling that uses commercial inputs that have to do with actual supply chain, who controls it, and what power sources are used are critical. Otherwise, we are about to follow our fantasy of massively increased consumption of multi-hundred kilowatt hour pickups and SUVs and massive vehicles. That's going to vastly accelerate our destruction of the planet.
Yeah, it seems to me that we're tailoring the solutions for a sort of preconceived notion of what life ought to look like. I mean, the most obvious thing to me is that our power grid is not set up for everybody to be driving an EV. It's kind of madness to me, especially in California when there are so many subsidies for electric vehicles, and yet the grid's not there yet.
I would ask people to simply do the following calculation. If between now and 2030, you want to have X number of EVs in California or the US, calculate the kilowatt hours of batteries required to meet that goal, where there's actually going to be production, and at what price, and you'll find it's China and it's coal-fired power. And then what size are those battery systems? And by the way, I drive a 44 kilowatt hour Chevy Bolt EV as my daily commuter vehicle. I tried to find, with a usable range, the smallest pack possible. But we should look at what they are. California and others, you know what they're actually incentivizing? Not smaller packs, but the largest possible pack.
I wonder how many kilowatt hours of electricity we produce in California per year.
And then look at what you need to produce to match that.
Right.
Because nobody's telling us. By the way, when they made the announcement in California that there would be kind of a period after which there would be no internal combustion engine cars, that very same weekend, it was announced that you shouldn't plug your electric vehicle in. I couldn't plug my electric vehicle in because they said, there would be power outages. There was limited power because of air conditioning. You're like, please tell me, like the adult, and do it in a transparent way. Answer these questions, please.
You're absolutely right about that. I remember it because it was one of the biggest PR flubs that I can think of in recent memory.
And I would say, if you can prove it to me, I'm ecstatic.
Sure, of course.
I'm ecstatic. I want to be proven wrong.
Yes.
But please engage in the discourse and show me, using transparency and rationality, what that is.
Yeah. All right. So the 21C, the VMAX, the Hyper GT, they're not inexpensive.
No.
They're very expensive cars.
Yeah.
99.99% of the world's population will never get in one. But down the road, is there a time when a regular guy is going to be able to own a Czinger?
I think you'll see through Divergent Technologies that this technology will take over chassis structures across, most of the automotive market. And 20 years from now, your city car, if we do this right, will be, engineered using this software, produced using AM, and assembled with our systems. And that technology will be more or less fully democratized. For Czinger Vehicles, for us, we want to always have the capital to put into the latest R&D generation and use those vehicles as that R&D test ground so that these vehicles can always push the performance boundaries. 10 years from now, we want to be pushing wherever that boundary is. That should be Czinger pushing it. So to a certain degree, I think we're going to stay in that kind of hypercar, supercar, advanced vehicle class, but it really is so that we can generate that R&D that'll eventually make its way into the rest of the industry as well.
Well, I'm looking forward to seeing what's in store. Kevin and Lukas Czinger, thank you.
Okay. Thanks, Maurice.
Thank you.
It's been our pleasure.
Great to have you here. Thank you.
That's all for this episode of Horsepower Heritage. Join me next Wednesday, June 7th, for a special episode of the show on the eve of the 24 Hours of Le Mans. It's a celebration of 100 years of the greatest motor race in history with my guest, author Richard Williams. If you like what you've heard, go to buymeacoffee.com/HP Heritage, and you can support the show for as little as $2 a month. So please consider making a donation. And tell your friends, write a review. All of those things help me reach more gearheads like you. Drop me a line at horsepowerheritage.com. Just click on the contact button there, and that'll get you where you need to go. So I'll see you back here next Wednesday. And until then, I'm Maurice Merrick. Thanks for listening.